go. Okay, we are going to get started. So I am recording a video for the AP Physics problem involving two dimensions, forces, and essentially we have a question where we have a box on a ramp and we want to find out something related to the motion of the object, some sort of information about that. So this is a great problem for our dynamics unit. It essentially brings in all of the different parts of this unit that you have learned. We need to understand vectors, how to break something up into from two dimensions into x and y dimensions. It involves Newton's laws, so forces, force is equal to mass times acceleration. It also involves friction, which is a major part of our forces unit, our dynamics unit. So I'm going to do this problem, and I'm going to try to show some key steps along the way on how you go about solving a problem like this. So anyway, the problem is we have a 25 kilogram box. It's released on a 27 degree incline. So what that means is like a ramp, basically. And it accelerates down the ramp at 0.3 meters per second squared. And the question is, what is the coefficient of kinetic friction? So I'm going to do a few things. I already did a couple things to kind of prepare this to explain for you guys. I also want to just briefly show you the method I'm going to be using to solving this problem. This is found on the notes that I provided. And I have this kind of pulled up to the side. So I'll be kind of going through this using this method as we do this today. So it says to start out by drawing an accurate free body diagram. You can see I sort of set up a little picture here, a side picture of this box on a ramp. And the basic idea here is that, we have an object on a ramp, and, I'm sure you guys know that if you have a ramp that's too steep, the object will start to slide on its own. And so here's a situation where the object is sliding. In fact, it's accelerating. It's getting faster as it's going down the ramp. And so we need to kind of think about the forces that are acting or applying to the box in a situation that is set up like this. So I have a basic drawing. One thing I want to explain is a little bit is the angles, because a lot of students have trouble with this. When you have a ramp, like a 30-degree ramp, and it says it's, oh, you know what? It should be 27 degrees, not 30. Let me fix that real quick. That's 27 and 27. So a lot of students have a hard time understanding the angle of a ramp is 27 degrees here if it's 27 degrees here. So let's talk a little bit about that. So this is my my x and y dimensions, okay? I like to use red for x and blue for y. And normally when we talk about dimensions, we like to think of up and down being the y. I like to use blue, and red is x, which is horizontal. In this particular situation, though, we're on a ramp, and so we're at an angle to the horizontal. In this case, our ramp is 27 degrees. And so if you think of this almost like a little windmill, a little pinwheel, watch what happens when I go from horizontal to the ramp's angle. So look at this line right here, okay? It's straight, right? I'm going to start to rotate this whole thing, and everything should be rotating. Every part of this little stick thing should be rotating the same number of degrees. So if I go click, 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 you can see that the angle right here that I have gone from perfectly vertical to what I have now is going to be the same as the amount of angle that I went from right here. In fact, let me draw this in. I'm going to draw a little horizontal line. And that's what we would normally refer to as 27 degrees, right? So if it's a ramp like this, it'd be 27 degrees like that. And you can see that this must have also gone the same number of degrees, 27 degrees. Okay? So keep that in mind when we're evaluating this problem. So I had this little picture set up to help us think about this problem. I also have what we're trying to find. It asks us in the problem, we want to find the coefficient of kinetic friction. And I'll circle that right now. That's a key thing we want to find. I labeled that right here just to identify at the beginning what we were looking for. So we want to find mu, which is the letter we use for the coefficient of friction. And then I put a little k after it, so mu sub k, to indicate we want kinetic friction. And I also found the equation in my notes for the force of friction because I thought that might be handy, right? Okay, so according to my steps, first step we got to do is draw an accurate free body diagram. So we're going to draw this right off this picture, and I'll draw another one off to the side so you can see a little more detail. The first thing we're going to add as a force on this free body diagram is the force of gravity. Okay. I'm going to label that F sub G. Force of gravity always acts down, near the surface of the Earth or a large object with mass. Force of gravity will always act straight down. Now, normally on a flat surface, we would have what's called a normal force, which is the ground pushing back. And if it's on the ground, the normal force would be essentially equal in magnitude to the force of gravity. But in this particular situation, when you have an object on a ramp, the normal force is not going to be equal to the force of gravity. It's actually going to only be equal to a portion of it. I'm going to draw the normal force. I'm going to label it F sub n like that. And the amount that the normal force is equal to is essentially going to be equal to a component of the force of gravity that is perpendicular to the ramp. So if I were to draw a little dotted line like I did right here, and I drew it all the way down until it hit a parallel line to the ramp like that, that's essentially how much the normal force would be. And you can go to the extreme scenario. What if you had an object on a cliff, right? What if our box was actually on a cliff and it was like, drawn right here? Well, the force of gravity would be straight down, and then there would be no normal force from the cliff because there is no force pushing down on the cliff to provide a pushing force back, Every force has an equal and opposite force. So if there is no force on the cliff from the box, because it's getting a force of gravity straight down, then there would be no normal force at all. And as you make that cliff more and more and more like a ramp, then the normal force will gradually get bigger and bigger and bigger until, if you have a perfectly flat piece of ground, then the normal force will be equal to the force of gravity. So that's my explanation for why I drew the normal force directly perpendicular to the surface of the ramp and why it's a little bit smaller than the force of gravity. Okay? Now the last thing I need to do is I need to think about the force of friction. This problem says that it's asking for a component of kinetic friction. Now, normally, if a problem is asking you to think about friction, they'd usually call it a rough ramp or a rough incline or a rough surface. In this problem, we're just going to have to assume that there's probably friction involved because it's asking about friction. But if it's a smooth incline, then generally you wouldn't need to worry about friction. You would assume friction is negligible. In other words, it's zero. But in this case, there is friction. And so right now you can imagine, okay, the box is going to be accelerating down. You could sort of see why that's the case, given that the fact the force of gravity is greater going down. But if there's a force of friction here at all, it's going to be acting against this motion, right? So if I were to draw my force of friction, it's going to be directed up the ramp. So I'm going to label this FR for force of friction. So there is my free body diagram. I'm going to draw this again now, and I'm going to draw this down to the side, just so we have a little bit more clarity. Okay, so here's my force of gravity acting straight down. I'm going to just outline the box just a little bit so you guys can see that. The normal force, like I said, is going to be equal to just the component of the force of gravity that is perpendicular to the ramp. That's how long I would draw this normal force. It's not like super critical that you get that perfect, by the way. Just that you know that it's perpendicular to the ramp, right? There's a 90-degree angle between the ramp, which I didn't really draw here, and the direction that the normal force is pointing. And then the last thing is the force of friction. Okay? And it's important to understand that we should have a net force acting down. So I didn't draw this friction force too great, because if I drew this arrow longer, it might actually cancel out what will inevitably be the force of gravity acting down the ramp. So I drew it pretty small just to make sure I had something left over if you're talking about net forces, which we are. So this is my free body diagram. Now note we have 3 forces acting on our box, right? And if I were to solve this problem using my standard axes, my x being perfectly horizontal and my blue y-axis being perfectly vertical, you can see that the only force that is technically in one dimension is the force of gravity, right? It's going straight down. All of its magnitude is in the y component. The force of friction, though, because it's at an angle to the horizontal, is going to have 2 components. It will have a little bit of it in the x and a little bit in the y. Same for our normal force. A little bit of it will be in the x and a little bit of it will be in the y. So we have 2 forces that are 2-dimensional, and we have 1 force that's 1-dimensional if we use our standard xy axis. And here's the trick that I have in my notes. If we rotate our frame of reference 27 degrees and match it with the angle of the ramp, take a look at what happens now. Now, our force of friction is in 1 dimension. Our normal force is in 1 dimension. That means that, you add, you subtract. It's super easy math, right? The only force that isn't in 1 dimension is the force of gravity. And so this actually halves the amount of work we have to do with trigonometry, breaking 2 dimensions up into its, single dimensions. And this makes the problem a lot easier, because down the ramp is literally a 1-dimension situation here. Unlike here, where down the ramp is going to the right and also down. That's a lot more confusing, and it will take a lot more math to do. So this is why I'm going to decide that my x and y coordinates are a little bit different. Let me just draw that real quick. So here's my x, and here's my y. Okay? And I'm going to say, I'm going to say positive x. Down the ramp is positive x, and up perpendicular from the ramp is positive y, just so it's clear. Okay. Now, we're not done yet with our free body diagram, so I'm going to break it up one more time. Actually, you know what? Let's do some net force equations first. So what we want to do is we want to think about what the net force is. First of all, the net force is not equal to 0 because it says in the problem that it's accelerating, right? So every net force is equal to an object's mass times its net acceleration, right? I just want to make that clear. But because this is a 2-dimensional problem, we have 2 components. We have an x component and a y component, right? That we just defined. So let's talk about what these are going to look like. First of all, the net force in the x component will be equal to the object's mass times its net acceleration in the x component. Same thing is going to apply for the y. So let's take a look at this situation, and let's rewrite this again. Let's look at all of the forces acting in each of these parts. All right, I'm going to draw this one more time. Here's our box. As we mentioned, we drew this situation so that the force of friction is in the x component. So that's nice. And we also drew this so that the net force, or the normal force, is in the y. It's only in the y. Let's use the same colors. So we don't need to do anything to these because they're completely in the dimension that they have been sort of highlighted as, or defined as. The only force we need to break up is the force of gravity. The force of gravity is going to have two components, right? So I originally drew the force of gravity straight down, and I'm breaking it up into its components. There's going to be a force acting along the x and a force acting along the y. Here's my force acting along the y. I'm going to draw it as a dotted line so you know that that is a component of the force of gravity. I'm going to identify this as FGY. Okay, so that's the force of gravity acting perpendicular to the inclined plane. And then we have another component, right, which is the x component, the component that's parallel with the ramp or the incline, that I'm going to draw right here. Which we'll call FGX. And together, those would create our force of gravity, our net force of gravity. I'm not going to draw it because I don't want to make it look like there's an extra force here. But you can imagine if I were to add these two x and y components together, I'd get a triangle, right? It would form like a triangle-like shape, and here's what the hypotenuse would be. So these are just the two sides of my force of gravity, two components of the net vector, the resultant vector. Broke it up. And now we're going to use this as our means of solving these two equations, okay? That's what I'm doing here. So, okay, let's look at the x first. And the reason why we want to look at the x is because the force of friction is in the x, and we've already recognized that the force of friction, we have the equation for it. So if we can just figure out an equation that has that, we can break it down and find this. So I wrote this up here, right? And we know the net force is equal to the net mass times the net acceleration. We also know that the net force is equal to the sum of all forces acting along that component. So I'm going to continue my equation I've been doing, and I'm going to put my two forces that are acting in the x component in here. Now, remember, we said that the positive x is down the ramp, and so you can see clearly that the force of gravity in the x component is going to be one of the forces acting in the x component for the net force. The other force is the force of friction, and because it's acting up the ramp, we're going to minus this magnitude. So the force of gravity acting down the ramp in the x minus the force of friction will give us the net force in the x direction, right? And if we have a greater friction, there could be a situation where the kinetic friction is so great that would actually cancel the force of gravity in the x out. And this would be a situation where our box or whatever would be slowing down as it goes down the ramp and stopping if those were exactly the same value, or if the force of friction, kinetic friction, was exactly equal to the force of gravity down the ramp, then our box would simply slide at a constant speed. That's not this situation, though. Our situation, we have a force of gravity in the x a bit greater than the force of friction, so that there's a bit left over when you subtract the force of friction. Okay, so this is our key equation. I'm going to just circle or make a little dealio around this, because this is actually the thing that contains the variable we're solving for, the coefficient of friction. However, it's still going to be useful for us to look at the force of the net force in the y, as you'll see in a minute. Let's look at all the forces acting in the y. We have the normal force, F sub n, minus the force of gravity, because it's down, right? Positive y is up, negative y would be down. So minus the force of gravity in the y. Okay. So let's continue here. Like I already said, we've already know that this is what contains our coefficient of friction. So that's what we want to break up. In fact, let's just rewrite this. Mass times the net acceleration. You might be asking, why didn't I write net force? Well, we don't really need the net force in the x. And because in the problem they gave us the mass and they gave us the acceleration, which remember, this is accelerating down the incline at 0.3. So we know that all of the acceleration is in the x down the ramp. None of the acceleration is up or above or below the ramp, because the force perpendicular going up is canceling the force of gravity acting into the ramp. So it's really only accelerating parallel to the ramp. And so we can say that this 0.3 is the net acceleration in the x. So we don't really need the net force in the x. Doesn't seem like that. So I'm just going to focus on the fact that the net force in the x is equal to mass times net acceleration. And then I'm going to rewrite force of gravity in the x. And that's going to be a troublesome thing, right? We can't really solve that yet. We need to figure out, what is that equal to? Minus the force of friction, which is mu k times the normal force. Okay, so let's review what we got. We know the mass, we know this. This is what we're solving for, but unfortunately we don't know these two things. We don't really know what the normal force is. We don't really know what Fg of x is. So let's go back to our free body diagram and think about this. The normal force, because the net force in the y has to equal 0, and I didn't actually make that clear yet on paper, but we just talked about it, right? The box is not falling into the ramp, and so it must have a net force of 0 up and down, above and below the ramp. Those cancel out. So the net force in the y must be 0, which means that the normal force must be equal to the force of gravity in the y. These two, if I move that to the other side, it becomes plus. So these two equal each other. And hey, that's great, because we can plug that in now, just in time. So Fgx minus mu of k. I'm going to put these in parentheses so you can see, what substitution I just did. Again, all I'm doing here is I'm saying, because the net force in the y is 0, that must mean the normal force here is equal in size to the force of gravity in the y. So I can just replace the normal force with the force of gravity in the y, because those, when they add together, they equal 0. So they must be equal to each other, but one's negative, right? So there we go. All right. Now, normally, when you think about the force of gravity, it's equal to mass times gravity, right? And that's true. That's absolutely true. But in this case, we're working with components of gravity, right? Force of gravity in the x, force of gravity in the y. So let's think a little bit about that. This is the force of gravity in the y, right? And here's our angle, 27 degrees. So when you look at that angle, this is adjacent, right? This is adjacent to it. And this angle, which is quite a bit smaller in magnitude, this is going to be opposite. So remember your SOHCAHTOA, sine, cosine, and tangent. If you are looking for the adjacent side, you use cosine. And if you are looking for the opposite side, you use sine. So let's go ahead and let's figure out what these things are equal to. Well, force of gravity, we know, is equal to mass times gravity. So that's what the hypotenuse is equal to. The adjacent side here is adjacent to that angle. So if I use cosine of theta, let me just try to make this as organized as I can. So cosine of theta is equal to adjacent over hypotenuse. The hypotenuse is going to be the force of gravity. And the adjacent side is going to be the y component, right? Because again, here is my line, this is my hypotenuse, this is adjacent to the angle. My FG of x is it's drawn up here in this free body diagram, but you could sort of think of it as this side too. It's going to be equal in magnitude. So it's a cross. It's opposite to the angle. So when I rearrange this whole equation, I get that the force of gravity in the y is equal to F sub g times cosine of theta. Okay? Now let's talk about FG of y. Oh, let's see, what did I do? My bad. Let me just relabel this. So this is FG of y. Let's do FG of x now. FG of x is opposite, so we'll use sine, which is opposite over hypotenuse. We've already identified that the opposite, or the hypotenuse, is just the full force of gravity. And the opposite in this case will be FG of x. Oops, let me get that up there. Okay, so full rewrite. I'm going to move, first off, here's what I'm doing. I'm moving the force of gravity over to sine. So I'm rewriting it. I'm multiplying the force of gravity times sine of theta is equal to the force of gravity in the x. And these are my substitutions I'm going to throw in to my equation up here. Okay, so let's make this very obvious. We have a lot going on at this point, but we're almost done. I'm going to draw one more arrow all the way down here. I'm going to bring this all together now. So I'm going to rewrite this whole thing. Mass times the net acceleration in the x is equal to, and I'm replacing the force of gravity in the x with the force of gravity times sine of theta. Basically, the part of the force of gravity that is acting horizontally, right? That sine theta is a fraction of 1. So when you multiply it by the force of gravity, you get a fraction of the force of gravity. So that's the fraction of the force of gravity that's acting in the x, this guy. And then I'm going to go minus the coefficient of friction times the force of gravity in the y, which I have found right here. So I'm going to substitute the force of gravity of cosine. So what I have effectively done is I broke up the one force that's in 2 dimensions, and I put it in the places that it had to go in my net force equation. This one had to go right here, to substitute for the force of gravity in the x, and to substitute for the force of gravity in the y, this one had to go right here. Okay. Let's wrap this up now. Oh, I'm glad I just highlighted that. Force of gravity is equal to mass times gravity. So we have one more substitution we can do. I'm going to replace the force of gravity with mass times gravity. We're going to use -10, by the way, for gravity, or 10, I should say. 10 meters per second squared, just to simplify it. Okay, so here is my full equation. Let's get this done. One interesting thing you might notice is that the mass of the box is actually in every part of our equation. So every term has the mass in it. So we actually can cancel this out, which is kind of neat. And this is a very big realization. If you have a ramp and you have a variety of boxes and they're all made of the same material, This would apply to, cars with the same material. They're all made out of rubber. They have rubber wheels, the tires. If you have a ramp or a hill or something, it doesn't matter what the mass of the object is when it comes to whether it's going to slide down the hill or not. This is why if you have a car trying to go up a hill in a snowstorm or an ice storm, pretty much any car is going to slip down the hill unless its tires are made out of something different, like it's snow tires that have a different type of rubber, or they might even have metal studs in them that act as like crampons, like little spikes. If you just have regular car tires, it doesn't matter if your car is heavier. It's going to slide just as much down a hill than any other car, a light car, a heavy car. This is true for anything. The mass actually cancels out of the equation. So the net acceleration is equal to g sine of theta minus mu, or this is what we want to solve for, times gravity times cosine of theta. So we want to get this guy, and we want to solve for it. To do that, why don't we move it over to the other side by plussing it, right? So I'm going to go mu of k times gravity times cosine of theta. And then I'm going to minus the net acceleration to the other side. So g sine of theta minus a net x. So let me explain what I did. I added to both sides this exact same term, which canceled it out on the right side. And I got mu of k times gravity times cosine of theta. And then I subtracted both sides by the net acceleration term, which moved it over to the right side, since it would cancel out on the left. I want to solve for the coefficient of kinetic friction. So now I'm just going to divide both sides by g times cosine of theta. Which cancels the g out on this side and cancels the cosine theta out. And I'm left with the equation that solves for mu of k. And what the cool thing about this is I don't actually need the mass of the box. That was given to me originally, almost like a throw out. Okay, so let's go ahead and solve for it. I'm charging my phone right now, or my calculator. Ooh, I think I have enough juice for this thing. All right, so let's go ahead and solve. I'm going to use, for G, I'm going to use 10. Just so you know. So let's go ahead and do that. So 10 times sine of 27 degrees. Don't forget to be in degree mode on your calculator when you do this. Minus the net acceleration in the x, that was the 0.3 we set, already explained why that was all in the x component. And then divide by 10, cosine 27. A lot of students might accidentally cancel the 10 out, guys, because they see it up here and up down here. But keep in mind, there's two terms on the top. So the only way you could cancel the 10 on the top and bottom is if this term over here also had a 10. So you can't, unfortunately, cancel that out. All right, so let's do this. 10 sine 27, just going to go step by step, minus 0.3, and then divided by 10 cosine 27. And previously, we already talked about what the coefficient of friction is. Shoot, I didn't think that got in camera. Let me just kind of go through that one more time. So 10 sine 27 in degree mode, minus 0.3, divided by 10 cosine 27. So the coefficient of friction is almost always between 0 and 1. A coefficient of friction of 0 means it's a perfectly frictionless material. A coefficient of friction of 1 means that it is just as hard to push slide an object horizontally by pushing it as it is to lift it. Now generally when you think about it, objects are easier to push horizontally, to slide them, than they are to lift. So if I had a really heavy box, it'd be easier to push it horizontally across the floor than it would be to lift it straight up. And so the coefficient of friction is always a fraction of 1. So in this case, about 0.5. It's about half as difficult to push this object horizontally across the floor as it is to lift it straight up. That's what 0.47, 0.5 means. So that's what I got. I'm going to round this to 0.48 since I already used a simplified term for gravity. It's probably going to be a little bit different than that, if we use 9.8. But that is my final answer. Let me just change the color here. And I'm going to go into my old key. I probably used 9.8 for gravity on this one. Looks like I did, but it turns out I got 0.48 there. It didn't get butchered enough to change the answer at all. So that's great. All right, now that was a very long video. If you watched the whole thing, congratulations. Didn't mean for it to be that long, obviously, but I tried to make sure I fully explained how to do this because I wanted to make sure I could explain every little part and some of the tricks that you can use for other problems. So just really quickly to kind of highlight the steps we did, we started by really thinking about the problem. We tried to think, what is it asking us to find? What does the situation look like? Make a drawing. We turned that drawing into a free body diagram. We broke it into its components, all the forces, there were 3. We broke it into its components in the easiest way possible, in this case by rotating our X and Y axes to match the angle of the ramp. We wrote our net force equations for both the X and the Y and used those broken up components to build those equations. We realized the Y component of the net force is 0, and we realized that the thing we want, the force of friction, is all in the X component. So by using this and just substituting all the things that are in there, like the force of gravity in the X and the normal force, boom, boom, force of gravity in the Y, we were able to build an equation that we could simplify enough down to solve for our coefficient of friction. And there it is, 0.48. All right, let me know if you have any questions.